So as far as the lecture, let me remind you what we did last time. So we're in the middle of learning dynamics, and we had this really cool result last lecture, which is that course-correlated equilibria are tractable. And they are tractable in a very satisfying sense, in the sense that there are simple, certainly computationally efficient learning algorithms. Specifically, we looked at multiplicative weights on Monday. And if all players use a no-regret algorithm like multiplicative weights, then the history of joint play will converge to the set of course-correlated equilibria. Okay, the biggest of the four sets in the equilibrium hierarchy that we've been discussing. Okay, so last time we proved in here, that's easy. All right? Now, the bigger an equilibrium concept, the more things there are to find, the easier it is to find one. So if any of these four sets of equilibrium were going to be computationally tractable, it was going to be the course-correlated equilibria. Okay, that's a necessary condition for anything else to be tractable. So today I want to look inward a little bit. I want to get greedy and ask, are any of these more refined equilibrium concepts also tractable? And so I want to cover two results today. The first result is we're going to get an analogous tractability result for correlated equilibria. Okay, so the next smallest set. And I'll remind you what these are in a second. Okay, so the first main result is correlated equilibria are tractable. Again, the sense will be similar. So there are again going to be learning algorithms. They're not going to be quite as simple. Okay, we're going to have to work a little bit harder, but they'll still be not too bad. They'll certainly be polynomial time, and the convergence will be in the same sense. If all players use these sort of more refined, what are called no-swap regret algorithms, then the history of joint play will in fact converge not just to course-correlated equilibria, but to the smaller set of correlated equilibria. Okay, so that's the first result I want to talk about. One quick aside, if you wanted to just establish polynomial time tractability, you don't actually need to resort to learning algorithms for course-correlated equilibria or correlated equilibria. You can formulate them as linear programs, which we can solve in polynomial time. So that has the benefit you even get an exact equilibrium, which you might recall from Monday we only got approximate course-correlated equilibria. It'll be similar today. But the drawback is, solving a linear program doesn't really bear any resemblance to actual behavior of players in games. Whereas the learning dynamics we're discussing, while not maybe exactly how people act, they at least bear some resemblance to actual behavior. Okay, so that's sort of the trade-off between the linear programming approach and the learning dynamics approach we're talking about this week. So looking ahead a little bit, we will talk some about a special case of Nash equilibria today, but next week we're actually going to talk about intractability of mixed Nash equilibria and pure Nash equilibria. So that's just to give you a little appreciation for, it's really cool, we can get tractability results for these slightly bigger sets, or non-trivially bigger sets. Okay, so let me remind you what a correlated equilibrium is. And I'm not going to give you the definition I gave you in lecture. Rather, I'm going to cite a definition that you proved as equivalent in an exercise a couple weeks ago. So this was exercise 59. So the original definition was in terms you think of a player sort of conditioning on its recommendation from a mediator and then switching and can it do better condition on its recommendation. This is the definition in terms of a switching function. So a distribution sigma over the outcomes of a game. I'll again use the notation for cost minimization games. So as a correlated equilibria, or just a CE, if for all players I and for all switching functions, so I'm going to use delta for that notation, this maps actions or strategies of player I back to strategies of player I. Okay, it need not be a bijection, it just maps actions to actions. So if for all switching functions, player I is no better off switching than it is just following the distribution sigma. Okay? So on the one hand, we look at I's expected cost according to the distribution sigma, and that should be no more than I's expected cost if every time it's supposed to be playing some strategy SI, it instead plays the strategy delta of SI. Okay. So this is the definition of correlated equilibria that maps most naturally to learning algorithms. Another thing just to remember about correlated equilibria, so if you just want a concrete example, this was the traffic light example, okay, where we had the stop-go game and it had two pure Nash equilibria, and we observed that you could implement a 50-50 mixture of the stop-go and the go-stop outcomes using a traffic light. That was essentially the mediator, which would recommend strategies via a green light or a red light, whether to go or stop respectively. Okay, so that's the equilibrium concept we're going to talk about in the first part of this lecture. All right, so last time, when we were talking about coarse correlated equilibria, we made this connection to these no-regret algorithms. So let me just remind you sort of what was the online learning setting we were talking about on Monday. So remember, this is where we have this known time horizon, capital T. And then on every day, little t, from 1 up to capital T. First, you have to pick a distribution. So again, we're just thinking about a single player at the moment. The single player has to pick a distribution over its actions. And then after deciding on the distribution, an adversary reveals a cost vector C sub t. Okay? And then the goal is to minimize your cost relative to some benchmark. And the benchmark we used on Monday was external regret, meaning you want to do at least as well as the best fixed action in hindsight. Okay? There's a connection between competing with the best fixed action and coarse correlated equilibria. So the motivating question for this first result is, all right, we have this refined equilibrium concept, correlated equilibria. Is there an analogous notion of regret, analogous to external regret, so that we again get this connection between the static equilibrium concept and a no regret notion? Okay, and there is. That's the next definition. It's called swap regret. And again, the point of this is so that minimizing this regret notion via dynamics will lead us to this equilibrium concept. Okay? So definition. So an algorithm, and here when I say an algorithm, I'm talking about, in this online decision-making setup that we talked about on Monday. So an algorithm has no swap regret if, for all cost vectors that the adversary might throw at us, and for all switching functions, so here A is the set of actions of this fixed player, this one player that we're thinking about, the expected value of how well you do, okay? So again, we're going to look at a time average. So how well you do is just the cost vector on time t evaluated the action you play at day t, which is drawn according to this distribution that you chose at the beginning of day t. Now previously, what we did is we looked at the best performance of any fixed action. Here we're going to look at the best performance under any fixed switching function delta. Okay, so we have a delta fixed. And we think about how well we would have done if every time on some day we played a given action, A sub t, we instead played the alternative action delta of A sub t. Okay. So this is a random variable because our actions are chosen at random from the distributions that we pick each day. Remember, our algorithms are randomized. But it has some expected value, and it should be the case that the expected value of this quantity is going to 0 for every switching function delta. So I forgot to say that. Goes to 0 as t goes to infinity. Okay. So this is only more stringent than the notion of external regret that we discussed Monday. External regret corresponds to needing to worry only about a subset of the switching functions delta. Namely, which ones? The constant functions. Okay? The functions delta that no matter what the input is, always outputs a fixed action. Okay, so if delta is a constant function, this is always the same action. So this is just saying your cost should be competitive with that of every fixed action, okay, as the time horizon goes to infinity. All right? So note, if you have an algorithm with no swap regret, meaning it vanishes, the time average vanishes in the limit, then it also has no external regret in the same sense. So no swap regret means no external regret. Okay? And basically this definition is engineered to make the following theorem true. Right, so this is so last time external regret was about competing with all fixed actions. Coarse correlated equilibria is just about not having any unilateral deviations that help you. Here we're talking about competing with all switching functions. Correlated equilibria is just talking about no switching function can help you. So the same theorem connecting the two holds today. So I'm not going to prove it again, but I'll state it informally because it is important. Okay, but the argument's exactly the same. So theorem. So what's not at all obvious is whether any algorithms of this type exist in the world. Okay? For all you know, there could be an impossibility result saying this is impossible. But suppose for the moment that there did exist such algorithms, and all players of now a multiplayer game used them. So if all players use no swap regret algorithms, then the history of joint play is indeed converging to a correlated equilibrium. Okay? So then sigma, so again, this is the same as on Monday. We just pick it as a uniform distribution over the t outcomes is an approximate correlated equilibria. Okay? And the regrets, which is going to 0 as t is going to infinity. The regret with respect to a given switching function in the learning algorithm just corresponds exactly to the error in the corresponding equilibrium condition for the exact same switching function. Okay? So as the regret's going to 0, the extent to which the error with respect to the correlated equilibrium conditions is also going to 0. Okay? Good. So they do exist. No swap regret algorithms. And what's great is we're going to be able to piggyback on the work that we already did on Monday. Okay, so I'm not going to show you the first ever no swap regret algorithm. There's some cool ones. But I'm going to show you a more recent, meaning last decade, reduction. And so we're just going to prove that if there exists no external regret algorithms, and I gave you one Monday, multiplicative weights. If there exists a no external regret algorithm, then there exists a no swap regret algorithm. Okay, so it's going to be a black box reduction from minimizing external regret to minimizing swap regret. So this is by Blum and Mansur, 05. Black box reduction from no swap regret to no external regret. Okay, so a problem we don't currently know how to solve to a problem that we do currently know how to solve. Okay. All right. So in particular, there exist no swap regret algorithms. This reduction will be polynomial time. Multiplicative weights is polynomial time, so there's even computationally efficient such algorithms. Okay, so corollary. There exists polytime, no swap regret algorithms. And combining this corollary with this theorem, we conclude that correlated equilibria are also tractable in the same sense as coarse correlated equilibria. Okay, there exist computationally efficient learning algorithms, so basically those that are output by this theorem. And if all players use these computationally efficient no swap regret algorithms, then we converge, the history of play converges to the set of correlated equilibria. Okay. So this is the big picture. So there's a few moving parts here, but you should know all the details for everything except for the proof of this main theorem. Okay? So I'm asking you to remember from Monday that we know that there exists no external regret algorithms, specifically multiplicative weights. I showed you the full description, the full proof. And then you should understand the connection. You should understand that no swap regret, if players use them as learning algorithms, lead to correlated equilibria in this sense. Okay? That's in the same sense, and with the same proof as on Monday. Okay? So that's why we get this conclusion. If we can prove this main theorem, then we get tractability of correlated equilibria. Okay? So that's where we are now. Questions about that?
Does the number of players
No. No. It's a fixed game. Yeah. So it's the same story with the number of actions. So we think of the number of players and the number of actions of each player, meaning the game. That's a fixed thing, and it's being played over and over again. Yeah. So like you might recall for multiplicative weights, we asked, how long does it take to get down to regret epsilon? And the answer was log of the number of actions n over epsilon squared. Okay? But we think of n as fixed and then t growing large. And then the question is, how large does t have to be as a function of the other parameters before you get a target regret? Yeah. Okay, then let's do the reduction. It's a cool reduction. It's a really it's something that you would hope would work, and so it's really cool that it does work. It does need one kind of great trick at the very end. Okay? But the high-level idea, I think, is very, very natural. It's sort of what you would want. It's the proof that you would wish would work. Okay? So here's how it goes. So like last time, n is the number of actions. And so remember, a hypothesis is that no external regret algorithms exist. Just think multiplicative weights. I'm going to need n copies of them. Okay, n totally separate instantiations of a no regret algorithm. So m1 to mn are different instantiations of, if you like, multiplicative weights, but it doesn't matter which one. Okay? Intuitively, the jth no-regret algorithm, mj, you can think of it as being responsible for protecting against deviations from action j to other actions. Remember, a switching function specifies. So what do we need to do to minimize swap regret? We need to say that our cost is at least as good as it would be if you applied any switching function to the actions that we took. Okay? And so a switching function takes as input an action, and it outputs an action. Okay? So there's sort of n squared things going on. And the jth no-regret algorithm is in some sense responsible for paying attention to the switches from the jth action. Okay? That's sort of an intuition to keep in mind. All right, so let me describe this reduction. Now remember how a no-regret algorithm works, what its input and what its output is. Right, so something like multiplicative weights, it spits out a distribution over actions, then you feed it in a new cost vector, it changes its internal state, like for example it modifies the weights, it spits out a new distribution, you feed it a cost vector, it spits out a distribution, and so on. Okay, so that's how we're going to be interacting with these M1 through Mn black boxes. Okay? All right. So these are subroutines at our disposal. M1 up to Mn. Okay? So they minimize, they have no external regret. Now, at the same time, we're designing this master no swap regret algorithm, which is responsible for outputting distributions over actions and receiving cost vectors. Okay? So, at the beginning of a time step, we ask all of our no regret algorithms, the external ones, for their opinion. What do you think we should do right now? Tell us a distribution over actions. Okay? So we're going to get, at a given time step t, an opinion from the first no regret algorithm. This is a distribution over the actions. This is what M1 thinks we should do. M2 will give us its opinion, and so on. Okay, so Q1t through Qnt, each of these is a distribution over the n actions. We have n distributions over the n actions. So we receive distributions Qt1 to Qtn from M1 up to Mn. The next step I am going to, until the end of the proof, leave underspecified, underdetermined. Okay? So the problem is, all these no-regret algorithms have their own opinion about what we should do. Okay, about the distribution from which we should pick an action. And in general, these are not going to be the same distribution. They'll have different opinions. But we're designing this master no swap regret algorithm, hopefully. And so we're responsible for outputting a single distribution over actions. So we have to somehow take these n distributions that are different and compile them into some consensus distribution over actions, which we then report back. Okay? So it's not clear how to do that. I mean, you could think about various ways, but it's not clear what the right way is. But that's the key trick, is the right compilation procedure. So for now, there's going to be some method by which we take these n distributions and compute a consensus distribution PT. Okay. So in our master algorithm, this is the central processing unit, if you like. It takes as input the n distributions, and it will somehow figure out the distribution from which an action eventually gets chosen. Okay? So this pink box is the actual no swap regret algorithm. Okay? So its job is to spit out distributions and accept cost vectors. Okay. So at time one, it's just going to do something like pick an action totally at random. Okay? So then we find out a cost vector. And now, of course, each of our subroutine no regret algorithms, M1 through Mn, they're also expecting a cost vector, right? That's how these guys work. So M sub j, it's unaware of anything else in the world. It doesn't know it's part of this big machine. It just is expecting to get a cost vector, spit out a distribution. It's Qt, get a new cost vector, and so on. So the next step in our reduction is to take the real cost vector from nature, from the adversary, and apportion it amongst these no regret algorithms, M1 through Mn. Okay? So after we say what our distribution of actions is PT, we receive a cost vector CT. Okay? And to the outside world, this is all that the outside world sees. Okay? We're outputting a distribution of actions PT, and then it gives us a cost vector CT. Okay? Everything else is internal to the guts of our algorithm and how we're interacting with our subroutines. Okay? So what do we do now? We're going to take this cost vector CT, and we're going to feed this into all of the no regret algorithms. Okay, well, not quite. Okay, we're going to split this. We're going to portion it according to the probabilities that we chose our different actions. Okay, so if we picked a given action with 10% probability, then the corresponding no regret algorithm gets 10% of the cost vector. So give the cost vector. Right, so remember, PT is a distribution of actions, our consensus distribution. Maybe action J we pick with 10%. So we just multiply the real cost vector by 10%, and we give that to the jth no regret algorithm. Okay, so in this picture, the overall algorithm gets CT as a cost vector, and now it's going to feed in. So this is going to be PT1 times CT. And it's going to feed in PT2 times CT, PTN times CT. Okay? And that's the entire reduction. All right? So you have these n no regret algorithms, each sort of responsible for switches from a corresponding action. Okay, the master algorithm, right, is responsible for outputting a distribution and inputting a cost vector. So what's missing is to specify the interaction. Okay, so how do you connect the outside world to your n no regret algorithms internally? Okay, and going outward, there's this magical box which has a consensus distribution PT from Qt1 through Qn. And then going backward, I've told you exactly how we split up the cost vector to go back. Okay, just according to the probabilities that we play the different actions. Question?
So is PT, that's a distribution over action?
Yep.
As opposed to distribution over distribution.
Right.
So when you're feeding back with cost in your sub black boxes, is it like each black box is kind of assigned to a single action?
Roughly. That's the rough intuition. Okay, so you could think about MJ as sort of paying attention or sort of guarding against switching functions that do really well by switching action J to any other action. Okay? Which is one of the things we need to worry about for swap regret.
It seems to me like what it might have
Well, they don't really know, frankly. Right? I mean, if you really think about just the I/O behavior of one of these neural grid algorithms, they literally just spit out a distribution and give you a cost vector, and it just goes back and forth. And as a function of the cost vectors that you tell it, it's going to modify what it tells you to do accordingly. So, I mean, so you're right in that, so I mean, you're correct in saying that this is fictitious. I mean, so these are not the actual costs. We're in effect lying to each neural grid algorithm about what the actual costs were. And it's not clear that's a good idea right now. But I guess, one thing that does seem sort of natural perhaps, another thing you could try is just feeding in this entire cost vector to each of the neural grid algorithms. But it also seems natural to kind of have the overall cost that you face to be reflected kind of in the superposition of the neural grid algorithms. Okay, to split up the cost vector between them. And then the probabilities that you were playing the various actions is a reasonable way to split that up. I'm not saying that's the only way you could do it, but I think it's reasonably natural as well. Okay, so let's just take stock of what we've got, and once we've actually figured out what we've got, we'll realize we just need one key trick, and we'll be done. Okay, so this reduction works for a suitable implementation of how to compute PT from the QTs. All right, so let's take stock. All right, so first of all, what is the expected cost of our algorithm? And again, I'm always going to do time average costs as usual, okay? Well, we incur cost every single day, days from T1 up to capital T. And then, expected cost, so there's a probability we play the various outcomes. And the probability that we play the various outcomes on a given day T is by definition this distribution PT, okay? That's what our algorithm decides to do. So we look over all of the actions. We look at the probability that we play a given action. And if we play that action, we just look at what cost we get. Okay? So that's what our algorithm, that's just its expected cost. Okay? Now, we want to say this is good. We want to say this is small. We want to say it's small, though, remember, relative to some benchmark. Okay? So relative to the expected cost under some switching function delta. Okay, that's our competition. So let's try to understand what those are. So what would our expected cost have been with some particular switching function delta? Okay. Well, it's almost the same thing. Let me call this expression 2 dot delta because it's with respect to a particular delta. So if every time we were supposed to play an action, k, we instead play delta of k, we just do the same sum. We just say, well, for any, what was the, look at the probability that our algorithm played action I. We're doing the counterfactual, where instead of playing I, what if we had played delta of I? So over here, we just look at the cost if instead of playing I, we played delta of I. Okay. So that's the expected cost of our algorithm if you applied the switching function delta to its history of chosen actions. Okay? Now just to make sure, all right, so we're trying to prove that this master algorithm has no swap regret. So what we're trying to prove, okay, so saying that our algorithm has no swap regret is exactly the same thing as saying that for all switching functions delta, our expected cost is at most the counterfactual expected cost under a particular switching function delta plus some little o of 1 term. Okay, and here by little o of 1, I just mean this is going to 0 as t is going to infinity. Okay, so for multiplicative weights, we had an expression like, square root of log n over square root of t. But the point was there was a t on the denominator, so when t got big, that thing went to 0. Okay? So this is, by definition, what it means to be no swap regret. Okay, so that's what we're trying to prove. All right, so that's what we want. What do we have? Okay, remember, we're trying to piggyback on the fact that we have these no external regret algorithms. Okay? So they're each providing some kind of guarantee, but with respect to these fictitious cost vectors. So let's look at what we just have already sitting on a silver platter for us. Okay. So let's now zoom in and adopt the perspective of a no-regret algorithm, let's say M sub j. Okay, M sub j knows about nothing else in the world. It's just spitting out these suggested distributions over actions, the QTJs, and it's receiving back these sort of scaled versions of the real cost vectors. Okay, so it's getting back PT of j times the actual cost vector CT. Okay, that's all MJ sees. It's no regret with respect to that data, okay, because it's a no regret algorithm. So since MJ is no regret, it's the case that for all actions, whoops, hold on, sorry. All right, so let's do the same exercise. So let's first think about MJ. What's its cost, or what does it think its cost is, and then we'll think about deviations. Okay? So MJ perceives its expected cost as, okay, so this is an expression indexed by j, so I'll call it 3.j. Well, what does it think's going on? Okay, so it's the same computation we did in 1, except we're doing it with what the distribution that MJ thinks actions are being played with, and with respect to what it thinks the actual costs are. And MJ thinks actions are being distributed according to QJ, and it thinks the real costs are these scaled versions of the CTs, okay, scaled by PT of j. So MJ perceives its cost to be the following. Again, you look at each day t, you'll get a given action I, and it thinks action I is being played on day t with probability QJT of I. Right? QJT is what it thinks, is what it's suggesting is the action distribution. And then what does it think the cost is when action I gets played on day t? Well, this is going to be the scaled version of the cost vector. Okay. So remember, no regret algorithm J gets the real cost vector scaled by the probability with which it was chosen in the consensus probability distribution. Okay. So again, that's exactly the same computation as in 1, except with different data. Okay. All right, so that equation would be true no matter what the algorithm MJ was, no regret or not. So the no regret hypothesis comes in when we argue that this is small relative to things that MJ could have done. Oh, bummer. So because MJ has no external regrets, its perceived cost is no larger than what it would have been had it taken some fixed action every single day.
Are there supposed to be PT of I or
What I do?
is it PT of I or PT of J?
Oh, yes, some of these, let me see. Yeah, the CT should be I think. This should be an I. That should be a J. Right, so we're talking about action I getting played. That's why we look at the ith component of the cost vector. But this, remember, this is just the scaling factor we're using on the cost vector. Yeah, so that's indexed by j, because the no regret algorithm is n sub j. Thank you. Good. All right, so now, because MJ is no external regrets, for all fixed actions K it could have taken every single day, its cost under the data we gave it is at most that what it would have gotten playing K every single day plus some regret term which is vanishing. So let me call this now 4.j, k, because it's got to be indexed by both the no regret algorithm J and the particular fixed action it's comparing its cost to. All right, so if from MJ's perspective, if it played K every single day, what would happen? Well, it would just get the kth component of what it was told the cost vector was. Okay, so we just replace that with a k. All right. So it's going to be pt j ct k plus some r sub j, which is just the regret term, which is going to 0. Okay. So again, for multiplicative weights, this rj would be root log n over root t. Okay. All right. So again, don't forget the goal. The goal is to prove that the master algorithm has no swap regret. So the goal is to prove that 1 is at most 2 delta, no matter what delta is. Okay. So what I'm now going to do is I'm going to sum this inequality. Okay, so we agree that the 3j, okay, the perceived cost of mj, is at most this, no matter what k is. All right, so I'm going to choose a particular k, and I'm going to sum over all of the no-regret algorithms, and we're going to be very close to the goal once I do that. All right. So again, remember, eyes on the prize, goal up there. For every delta, 1 is at most 2 dot delta. So fix some delta. So sum the inequality. All right, so we have this inequality over the choice of the alternative fixed action being delta of j. So remember, I'm considering a fixed switching function. So what I'm doing is for each no-regret algorithm, m sub j, I'm considering now a particular fixed action, namely delta of j. Okay, exactly the action suggested by this switching function. Okay. So now let's sum, right? So we know that this is at most this plus the plus the regret term. I'm just going to sum those over all j. Okay. So what do we get? All right. Well, on the left-hand side, we get the sum of these things. All right. So I'm going to go ahead and sneak the sum over j inside. Okay, it doesn't matter. And what do we have? We have the same stuff. Right? Q, J, I. Okay, so that was harmless. Just sum the left-hand side over all the no-regret algorithms. And we have that this is at most this with k now replaced by delta of j. And then plus all these regret terms. Okay. And because each of the rj's is going to 0 with t, and we regard n as fixed as t goes to infinity, the sum is also going to 0 as t goes to infinity. Okay. Now, have we made any progress? Okay, so what did we do? We just stated what we wanted. That was 1 and 2. Then we stated what we've got. That was 3 through 6. And so exasperating. All right, so check out 6 dot delta and 2 dot delta, which is a little bit hidden. Okay? So 2 dot delta on the left, 6 dot delta in the middle. Okay? Those are the same thing, okay, up to this little of 1 term. All right? So we stated what we wanted, and we stated what we have, and the right-hand sides are exactly the same. Okay? So if we can make the left-hand sides exactly the same, we're done. Okay? That just means the reduction works. Okay? It's just a consequence of the no external regret algorithms M1 through Mn that the big black box, the master algorithm, has no swap regret. Okay? So we just got to make the left-hand sides the same. The left-hand sides are 1 and 5. Okay? If 1 and 5 happen to coincide, we'd be done. Everyone agree? What's that? Some typos?
I just forgot to put one summation. Yeah.
Oh, did I? Oh, okay. Sum over j. Okay, good. right, that was the whole point. All right, so now do 1 and 2 look the same? One's an I and one's a J, but that's okay. Okay, so all we got to do is, so everyone agree, if 1 and 5 happen to coincide, we'd be done. Okay? We'd literally just be able to piggyback on the no external regret of M1 through Mn and conclude no swap regret for the master algorithm. Okay. All right, so I still haven't told you how to compute the consensus distribution P sub t from all of the suggestions Qt1 through Qtn. Okay? So the final trick in the proof is to notice, or to prove, that there's a way of computing the consensus distribution PT so that 1 and 5 become exactly the same number. Okay? All right. So how to do that? So again, remember, definition of P is under our control. Okay, so everything we've derived is a generic derivation in terms of P. Okay, we can pick P however we want. Okay? The Q's are given. Those are just popping out of the black boxes, M1 through Mn. But P we get to compute however we want. Okay, so how do we match 1 with 5? Okay, so if we can choose the PTs, remember we choose one of these every day, so that 1 equals 5, we're done. And we're going to do this in sort of the most, the way that you'd hope would work, right? So this is just a sum over the days t, sum over the days I. Okay, so for each summand, there's just some cost of this action I on this day t, has some coefficient, PTI. We don't know what it is. We have to figure out what to make this, okay? So CTI has some coefficient. Over here, same deal, okay? For every day t, for every day I, we have a term, the cost of that action I on the day t, and it also has a coefficient. It's a little more complicated, but whatever. Oops. Okay, CTI also has this coefficient involving this sum over j. Okay? So let's just see if we can compute PTs, actually just even independently each day. So let's just try to, on each fixed day t, compute a PT so that these coefficients match for every single action I. So sufficient for each t, compute the consensus distribution PT so that the coefficient in 1 equals the coefficient in 5. And that should be true for every I. So this is the great trick. And actually, probably, I wouldn't be surprised if a couple of you see the great trick. Is this an equation you've seen anywhere else? What's up? Yeah, good. Is it maybe even a specific kind of steady state of Markov chain? Bingo. So here's the great trick. So let X be a Markov chain. Okay, so I just mean like a directed graph where at a given node it specifies probabilities of which node you go to next, and it's memoryless. Okay, so all you need to know about where you're going next is where you are now. So Markov chain states are just 1, 2, up to n, the actions. And then the transition probabilities are given by the QJs. So again, remember, P's are what we have control over, Q's we don't. Q's are just sort of popping out of the no-regret algorithms. So the QJs are going to supply the transition probabilities. Okay, so for a given arc from a state J to a state I, that's going to be labeled by qj of I, this day t. Okay? So basically what we do, so remember, a no-regret algorithm on a day t, right? So the no-regret algorithm j gives us qj, and that's a distribution over actions. So we just interpret that as the transition probabilities out of action j, okay, to all the other actions. Okay? So our goal, our equation in the P's, is nothing more than the equations governing steady state distributions of Markov chains. Okay? So with this Markov chain, where the states are the actions and the Q's supplying the transition probabilities, every stationary distribution P, or every stationary distribution of X, satisfies star, where by star I mean that yellow equation. Okay? And many of you will have studied this, but just to remind you, so every Markov chain has a stationary distribution, at least one, and you can compute them in polynomial time. It's just an eigenvector computation. Okay, so this is something you can actually do in a computationally efficient algorithm. So going back to the algorithm, how do you actually compute the consensus? You form this Markov chain, use these as your transition probabilities, compute your favorite stationary distribution, and you spit that out as PT. Okay? Because that satisfies that equation there, 1 and 5 coincide, so the external regret guarantees immediately give you the no swap regret guarantee for the master algorithm. That's it. Questions? I mean, maybe sort of, in hindsight, I mean, once you have the reduction idea and you follow this argument, it becomes clear that this is exactly what you need, just to make the proof go through. But, if you think about, what are ways you could try to take a bunch of probability distributions and compile them into consensus distribution, in hindsight, maybe this isn't so unreasonable. Okay, what does this really mean that we're setting PT in this way, given the QTs? It basically means, okay, so we're trying to figure out which action to play at day T. And we start from an arbitrary sort of expert, if you will, an arbitrary no-regret algorithm. And we say, what do you think? What do you think we should do? And if you imagine this algorithm MJ sampling from QJ, it's QJ at this day T, maybe it says, I think you should play action 17. And now we iterate. So now we go to the 17th no-regret algorithm, and we say, what do you think? And it's going to sample a recommendation from its distribution, Q17. It says, I think you should play action 23. We go ask 23 for its recommendation. And then we go and we go and go and go and go. Okay? So the limit of that process, where you iteratively ask people for advice, and you sort of chase pointers according to who they say you should play or what they say you should play, that process is trying to converge, and it will converge in an ergodic Markov chain to this distribution P sub T. Okay, so that's the consensus distribution. You just iteratively ask people for advice where the Q sub J's are the distribution specifying what advice you'll get from a particular expert, a particular no-regret algorithm. Okay? Okay. So, again, the high-level point here, what we just proved, is that the set of correlated equilibria is also easy. Okay, so again, the algorithm obviously isn't as simple as multiplicative weights, but it's not that bad. It's polynomial time. And it, again, converges in a polynomial number of iterations to something with as small a regret as you like, as close to a correlated equilibrium as you like. So what I want to do next is I want to zoom in even further. Okay? So the good theorist is never complacent, always greedy, always wants more. So what about this set? Can we get tractability here? So in general, the answer is going to be no, and we'll talk about the sense in which the answer is no next week. But what I want to do in the remainder of this lecture is talk about a special case where the answer is yes for mixed Nash equilibrium. So I want to talk a little bit about two-player zero-sum games. So we chatted a little bit about zero-sum games even all the way back in lecture 1. We talked about rock, paper, scissors. So zero-sum games are sometimes called games of perfect competition. They're where players always want the opposite things. For example, one wins, the other loses. So rock, paper, scissors. You could describe as a matrix where in each entry you actually only need to bother to write one number, not two. There's two players, but the second player's payoff is just going to be the negative of the first one. So I'll write it so that it's the row player's payoffs in here. So because paper beats rock, for example, that's a 1. Scissor loses to rock, so that's a -1, and so on. And in general, I'll use the notation Aij, the entry of a matrix, to be the payoff that the row player gets. Okay, so the negative payoff of the column player. And it's been a while since we've talked about just mixed strategies that weren't correlated. So just to remind you, when we're talking about mixed Nash equilibria, each player is just responsible for picking a distribution over its strategies, and now the players randomly choose their strategies independently. Okay? So mixed strategies are just going to be an x and a y. X is a distribution over the rows, y is a distribution over the columns. And then as far as just writing down expected payoffs of players under a given set of mixed strategies, that's often convenient to write in matrix notation. So the expected payoff of the row player, for example, so the probability that a given outcome ij occurs by independence of the random choices is just the product of the probabilities that row I is chosen and that column j is chosen times aij, whatever the payoff to the row player is in that particular entry. So you might want to think about the matrix A. And as the distributions x and y over the rows in matrix format. And in general, we can write this as x transpose A, where A is the matrix of row player payoffs, times y. Okay? So that's just a little convenient way of discussing expected payoffs in zero-sum games. All right. So I want to talk about the Minimax Theorem, a sort of famous, awesome result. So suppose it's a zero-sum game, rock, paper, scissors, or something else, like where if you win, the other person loses, and vice versa. Typically, you think about these kinds of games as being played simultaneously, where both players sort of move at the same time, like in rock, paper, scissors. What if players have to move sequentially? Okay, but to make it non-trivial, so in rock, paper, scissors, if I make you move first, and I make you pick a deterministic strategy, obviously all is lost. Right. So what if I make you move first, but I only force you to commit, like in the online learning setting. I force you to commit to a distribution. Okay? So you commit to a distribution, and then the second player presumably is going to respond in some optimal way to make them as well off as possible and you as worse off as possible. Okay? So if the players have to go one at a time in a zero-sum game, would you rather go first or second? You want to go second, right? I mean, if you have to go first, you got to do something. And whatever it is you do, you could still do if you went second, right? And maybe you can do something better if you go second. Maybe you can adapt to what the other person did when they did something first. So it's clear that there's only a first mover disadvantage in zero-sum games, all right? Or rather, if either player has an advantage, it's going to be the second player. So the Minimax Theorem actually says that it doesn't matter. It's kind of amazing. I mean, it's amazing enough that the mathematician Borel, who you might know from the Measure Theoretic Foundations of Probability, when he realized the existence of Nash equilibria in these games was equivalent to the Minimax theorem, which was obviously false, it caused him to sort of abandon the study of Nash equilibria in these games. It was clear they couldn't exist because the Minimax theorem had to be false. So it's very counterintuitive back then and now. So what do I mean it doesn't matter? I mean, say you're the role player, and say I make you go first. That's you're trying to have your expected payoff as high as possible. So you're going to assume, of course, that the column player who goes after you will do the worst thing for you, minimize your payoff. Given that, you do the best thing possible. That's exactly the same as if you get to go second. So meaning the column player goes first, plays optimally, knowing that you'll respond in your own interest, and you get the same number. This is the sense in which it doesn't matter who goes first in a zero-sum game. Okay, where the x and y here, all these maximums and minimums are over probability distributions over the respective action set. Okay? So von Neumann originally proved this in the 1920s using relatively heavy machinery, given what we know now, using Brouwer's fixed point theorem. He proved it again in the 1940s using arguments which are basically equivalent to strong LP duality. That's why when a very nervous George Danzig went to von Neumann with his then very new simplex algorithm, von Neumann was able to just stand up in the middle of the meeting and give him an impromptu lecture on LP duality, which he just invented. So he proved it again in the 40s using that. These days, and what I'll show you now, is we can actually just deduce the Minimax theorem as a consequence of the existence of no regret algorithms, actually merely no external regret algorithms. So that multiplicative weights proof, that's sufficient to derive Minimax theorem, as I'll show you now. As we discussed, one side of the equation is clear. It's only worse to go first. Because whatever you do here, you can equally well do there if you want. Okay? So I'm going to focus on the reverse inequality. So proof. Take your favorite zero-sum two-player game. Just have both the row player and the column player play their favorite no external regret algorithm. Play them long enough so that the regret gets down to epsilon. So for example, for multiplicative weights, play for log n over epsilon squared steps, okay, where n is the number of strategies of the players. So until the expected regret, and again, external regret is fine, at most epsilon. So let P1 up to PT and Q1 up to QT be the distributions that these players' no regret algorithms tell them to play actions from. So for example, if they're running multiplicative weights, the P's and Q's are just proportional to whatever the current weights are in multiplicative weights at that stage. Okay. So just to be clear, so no regret algorithm, I guess a couple of things. So first of all, when I talked about no regret algorithms, and multiplicative weights in particular, I did it for costs. You can equally well do it for payoffs. That's going to be on exercise set number 9, in particular multiplicative weights. You just tweak it slightly, it works equally well for payoffs. That's the version I'm going to use here. No regret with respect to payoffs. The second thing is no regret algorithm. What does it do? It outputs a distribution. It accepts a cost vector, in this case a payoff vector, goes back and forth. So just to be clear, what are the payoff vectors that these players feed into their no regret algorithms to get advice about what to play at the next step? They just look at what the other player played at day t, and then they just think about, okay, well, if I had played my various actions, what would have been my expected payoff given the mixed strategy that the other player played at that time step, on that day, okay? So where, again, for the purposes of defining the no regret algorithm, the payoff vectors at time t, so for the row player, so remember A is just the matrix of payoffs. So if the column player randomized according to QT at day t, then after day t you look back and you say, oh, well, what would my expected payoff have been of each of my rows, given that the column player randomized according to QT? So that's what you feed in the no regret algorithm for the row player. And similarly, the column player, after the dust settles on day t, it says, oh, that's how the row player plays. That means this is my expected payoff of my various columns. That's the payoff vector you feed into the column player's no regret algorithm. Okay. Good. So now I want to argue that just the time averaged P's and the time averaged Q's, those form basically a min-max pair up to a small error. They're going to basically prove up to 2 epsilon this equation. Okay? So these no regret algorithms just basically hand us certificates of this equality. So let x hat, again, this is just sort of the time averaged mixed strategy that the row player uses over these capital T days. Similarly, y hat is just, in some sense, the time averaged strategy used by the column player. Also, let V denote the expected payoff of the row player. Sorry, actually time averaged expected payoff. Let me actually just write down the formula. Yeah. Okay. So on a given day t, by definition, the row player randomizes according to PT, the column player randomizes according to QT. So for fixed t, this is exactly the expected payoff that the row player got on day t. And then I just time average that expected payoff over the capital T days. Okay, that's going to be V. Good. All right, so how does the no regret condition come in? So player 1 ran its no regret algorithm, and this is its time average payoff V. No regret says it couldn't have done much better if it had used any fixed action, meaning a fixed row. So if instead of playing P1 then P2 all the way up to P capital T, if it had just played row 12 every day, it could have gained at most epsilon in the payoff, in the time average payoff. Okay? So player number 1, since its expected regret is the most epsilon, fixed rows I that it could have played every single day, we have that right. Yeah. Okay. So if it had played, so this is just meant to denote deterministically playing row I every single day, little t. The column player is doing what it was doing before when we think about the regret. So this is QT. Okay? Sorry, there's no t here. That is a transpose. Oh, boy. Sorry about the conflict between the time horizon and transpose. So this is the transpose of the ith basis vector, indicating deterministically playing row I. Okay? So this is not indexed by the day. Okay? This is just the same action over and over again. Remember, that's the external regret benchmark. Okay? So this is the same thing. So the column player is doing what it was doing before, playing distribution q little t on day little t. Since this is fixed, this is the same thing as just playing against the time-averaged version of the column player's strategies. Okay, so this is just transpose of the ith basis vector times the payoff matrix times y hat. Okay? And because it's no regret, had it played the same action every single day, it only could have gained epsilon. Okay, so this is at most v plus epsilon by the no regret condition. All right, so the upshot, any fixed row, okay, had you played it, would have netted you at most v plus epsilon. That means any fixed mixed distribution, okay, which is just an average over rows, also would have netted you at most v plus epsilon, had you played it every single day. Okay? So thus, we'll call this A. So this is now an arbitrary mixed distribution for the row player. But of course, that's just an average over various deterministic row strategies. So because this inequality holds for every fixed row strategy, it also holds for every distribution. Okay? So no regret implies that if you could go back in time, pick your favorite mixed distribution X, play it every single day, you could only gain epsilon over what you got from your no regret algorithm. So that's from player 2's perspective. From player 1's perspective, it's happy. Any mixed strategy wouldn't have done much better. Now, how do we use it at zero sum? Okay? So that means the column player's payoff is the negative of the row player's payoff, or equivalently, the column player is trying to minimize this number while the row player is trying to maximize it. Okay? So now by symmetry, because it's zero sum, the exact same argument says, well, the column player was also running a no regret algorithm. Okay? So by the same argument, any fixed column could have decreased the row player's expected payoff by most epsilon. Maybe you could have gotten down to v minus epsilon, but no lower than that, okay, by the no regret hypothesis. And again, if that's true for every single fixed column it could have played every single day, it's true for every single mixed strategy over columns that it could have played every single day. Okay? So the same argument for player 2 says, since the regret's at most epsilon, there's no way that the column player could have dragged player 1's expected payoff down further than v minus epsilon. Okay? So for all distributions y over column strategies. And so now we're pretty much done. So now I claim x hat and y hat witness up to a 2 epsilon this equation, or rather the non-obvious version of this equation. So again, remember, no surprise that the right-hand side is bigger. Now we're going to show that the right-hand side can only be bigger by 2 epsilon. Okay? So thus, So let's start with the left-hand side. So if we instantiate x, this only becomes smaller. So let's just use x hat. Okay. Now by b, pretty much for fixed x hat, the best the column player can do, okay, with the best response, with an optimal y, is to save an epsilon. Okay, is to get this down to v minus epsilon. By the same token, if we think instead about the column player playing according to its time average y hat, and we let the row player do its worst, pick its optimal mixed strategy, we know the row player with an optimal mixed strategy can only get itself an extra epsilon beyond v. Right? So that was inequality A. Okay? So for all distributions x, in particular for the best of them all, the expected payoff of the row player is at most v plus epsilon. Okay? And so now, of course, if I minimize over y, this only becomes less. Now, epsilon's arbitrary. Right? We can put epsilon as small as we want. We just jack up capital T to, for example, for multiplicative weights, T over epsilon squared. But you give me the epsilon, I'll give you a long enough amount of time to run the multiplicative weights algorithm that you can exhibit x hat and y hat that show that these two quantities can be at most 2 epsilon apart. Okay? So taking the limit as epsilon going to 0, there can never be a gap between these two quantities. It has to be equal. Questions about that? So this is the min-max theorem. I mentioned how there was a connection in Nash equilibria, and that's why Borel got discouraged. But just to be clear, if you look at these two inequalities, A and B, they in effect say that x hat, y hat is approximate Nash equilibrium. Okay, so if the row player plays according to x hat, and the column player plays according to y hat, neither one can change the payoff or can make the payoff better in their favor by more than an epsilon. Okay, so you gain at most an epsilon. So it's an approximate Nash equilibrium. But again, we can take epsilon as small as we want. And so by a limiting argument, there has to exist an exact Nash equilibrium. And again, more generally, it takes quite heavy machinery to prove existence of Nash equilibria, like Brouwer's fixed point theorem. Or historically, this is proved for zero-sum games using LP duality, but it's just a consequence of these no-regret algorithms. Have a great break. See you in 12 days.